An electron is initially moving at a speed of 1.79 times 10 to the third meters per second directly toward a long wire that has 2 amps of current flowing through it. The electron is 2.5 meters away from the wire. What is the magnitude of the force exerted by the magnetic field on the electron? Now, a couple of things first. It says that it's an electron, so we got to make sure we keep that in mind because an electron has a negative charge and will behave oppositely to that of something that is positively charged. So let me just go ahead and draw a picture of what we have right here. So I have a wire carrying current. It doesn't really tell us, but it just says that we have a current of 2 amps and that an electron is being projected straight for it. So it has a velocity like that going straight towards the wire. The velocity is this value right there, and the current distance away from the wire when we're doing this problem is 2.5 meters. Okay, so that's the distance away at this moment in time. Now, if we take a look, the wire is carrying current up. Now remember, if we're looking at a wire carrying currents at us, so this is I at us, remember it forms magnetic field lines around it that are circles. So if you imagine grabbing that wire with the thumb pointing at you, your fingers would move in a counterclockwise direction around the wire. Okay, so imagine that there's these circles that are going around. Now it's kind of hard to do this in a two-dimensional plane, but there's like a circle kind of going around like this around the wire. And at this moment in time, so here's what I want you to do. Everybody just kind of grab the wire with your thumb pointing up. So your thumb's pointing up, grab the wire. You'll notice that when you point to where the electron is, your fingers will be going into that side. So the magnetic field is into the, I was just going to say it's into the board on this side, according to my current. Now, if the current was flipped the other way, then the magnetic field would be the other way. The key idea about this is that if that is into and the electron is projected straight towards the wire, you know the angle right now is 90 degrees. So how do I go about determining the magnetic field at a distance of 2.5 meters from the wire? So this is what I'm going to do. I'm going to say the magnetic field around the wire, remember, is mu naught I all over 2 pi r. We know mu naught is a constant. I is given. That's the current in the wire of 2 amps. And then R is the distance away from the wire. It just so happens that the electron is 2.5 meters away from the wire at this moment in time. So I could plug into all that and get a numerical value for the magnetic field. But what I'm going to do is I'm going to go ahead and plug that into the force on a charge moving through a magnetic field. And so remember, that's the first formula we learned in this unit, that QVB sine theta is how I determine the force on a moving charged particle. Okay, so it says, what is the magnitude? Now remember, magnitude is just the size of the force exerted by the magnetic field on the electron. Where is that magnetic field coming from? It's coming from the current carrying wire. This guy is producing a magnetic field right there. So what I'm going to do is this would just be the charge of an electron. The velocity we already know. B would be given by the formula mu naught I all over 2 pi r. Okay, so basically that's the field produced by the wire. That's the field that this guy feels. And then we said that sine theta would just be 1 because the angle is 90 degrees and sine of 90 is 1. So I'm going to plug into this formula. Go ahead and plug in and then we'll get the answer. So we know that the charge is 1.6 times 10 to the negative 19th coulombs, absolute value. It would be a negative because it's an electron, but that's okay. The velocity is 1.79 times 10 to the third meters per second. That's my velocity. Okay, I'm going to have to come down here to finish that out. So mu naught, so imagine that this is right there. Mu naught is the 4 pi times 10 to the negative 7th Tesla time meter over amp times the current, which we said was 2 amps. All over 2 pi times the distance. The distance, we said the electron is from the wire, is 2.5 meters. So if I plug all that in my calculator, we get 4.58 times 10 to the negative 23rd newtons. Now it does say we want to find the force, but I don't need to worry about the direction. The reason I don't need to worry about the direction is because it said what's just the magnitude. Now, if it did say the direction, well, if I take a look, if that is into and that object is going to the right and it's negative, I would use the left-hand rule. So I would point my thumb to the right. I would point my fingers into into the page, and I noticed that my palm, my left palm, would be facing in the same direction as the current. So the direction would be the same as the current, but it didn't ask for that. That's just a little side bonus. The next question says that we have 3 parallel wires are arranged in a partial square configuration as shown in the diagram. In 2 of the wires, 5 times 10 to the negative 4th amp current flows towards you. So that would be this guy. I'm going to go ahead and call that one I1. And this guy, I'll call that guy I2. Those are both 5 times 10 to the negative 4th amps. So go ahead and write that in just to help us out. All right, and then it says a current flows toward you. And in the third wire, 7.5 times 10 to the negative 4th amp current flows away from you. So this would be the one that's flowing away from us. So that's 7.5 times 10 to the negative 4th amps. And I'll call that I3. What is the strength, and in parentheses says, don't worry about the direction, of the magnetic field at the point P of the missing corner of the square? Okay, so the nice thing about the square is we know that every side has that value. Okay, so all 3 of these wires are communicating to that spot. Well, let me go ahead and do this. In blue, I will draw the circle that's associated with that. Remember, the wires are the center of the circle. So if I think of that as being the center, then the blue represents the magnetic field due to that guy right there. Okay, it would form that circle. So at that spot, it would be going up. Now, how do I know it's going up? If I grab the wire with my thumb facing me, my hand would be moving in a counterclockwise direction. So this would be B1. Okay, let's look at I2. We'll do this in green. So I2 is the center. If I imagine that there's a circle right here, it'll move around like this, right? And so there's the circle, there's my radius for that particular thing, and so P is at R away. And as it moves, if I grab my thumb facing me, you'll notice that my hand works in a counterclockwise direction. At the top of the circle, it would be directed exactly to the left. There is B2. All right, now B3 is a little bit more tricky because it's at the corner, but it still forms a circle. So I'm going to do a circle here for this guy right here, okay? That's my circle for this particular thing, but his radius is that right there, which is not just 5.36 centimeters. If you notice, it would actually be 5.36 that way and 5.36 that way to get that distance away. Now, because current is going in here, I would point my thumb into the page, and I noticed that that would be in a clockwise direction. So it would be like this. Well, at that spot, it would point exactly tangent to the path. Now, this is kind of cool because this is a square, right? That angle right there, if I go ahead and go back and draw in a coordinate system, that angle should be a 45-degree angle because that angle and that angle are 45, or that angle and that angle are 45 because of how it splits, right? And so we're able to determine that that would be a 45-degree angle. I am going to call that B3. All right, so let's calculate all these. B1 would be mu naught I1 all over 2 pi R1. I1, so I'm just going to keep this as mu naught. I1 would be 5 times 10 to the negative 4th amps. 2 pi, the distance that this guy is to there is just 0.0536 meters. Okay, so if I plug in 4 pi times 10 to the negative 7th there and then multiply this out, I would get 1.87 times 10 to the negative 9th Teslas. All right, so that's B1. Now, here's what's kind of cool. B2, which is that one, the green one right here. The green one is B2, formed from wire I2. Okay, it has the same distance as well as the same current. So we can actually say that this is the same thing as B2. So B1 equals this value, which also equals B2. Now, the only difference is B1 points up and B2 points to the left. So now let's look at B3. So B3 is a little bit different. It's still mu naught times I, but now it's I3, which is a different current than 1 and 2. And then it's 2 pi R3, which is a different distance than R1 and R2. So that is 4 pi times 10 to the negative 7 Tesla times meter over amps. I3 is the 7.5 times 10 to the negative 4th amps. Amps and amps will cancel. all over 2 pi. Now, R3 would be 5.36 squared plus 5.36 squared, square rooted. So if I do that really quickly, 5.36 squared plus 5.36 squared, and then square root that, I get 7.58, which would be 0.0758 meters is that value. So if I punch all this in, I'll do that really quickly. It's 4 pi times 10 to the negative 7th times 7.5 times 10 to the negative 4th divided by 2 pi, and then divide that by 0.0758. And we get 1.98 times 10 to the negative 9 Tesla. Now that points at an angle. Now it just so happens that that angle is 45 degrees. The cool thing about 45 degrees is cosine of 45 equals sine of 45. So B3 in the x direction would be B3 cosine of 45 degrees. And then that also equals B3y, which equals B3 sine of 45 degrees. So I'm only going to have to punch this in once. So B3 in the x direction, which equals B3 in the y direction, equals 1.98 times 10 to the negative 9th Tesla cosine of 45 degrees. If I then do that, I get about 1.4 times 10 to the negative 9th Teslas. Now, B3 in the x direction is to the right, and B3 in the y direction is down. Well, to the right and to the left will cancel out, all right? And then down and up will cancel out. So let's go ahead and do this. B in the x direction would be B, let's go back, B2 plus B3 in the x direction. I'm going to call to the right positive, and I'm going to call up positive. So if I call right positive, B3 in the x will be positive, but B2, which points left, will be negative. So it's a negative 1.87 times 10 to the negative 9 Teslas plus 1.4 times 10 to the negative 9 Teslas. So negative 1.87 times 10 to the negative 9th plus 1.4 times 10 to the negative 9th. I get a negative 4.7 times 10 to the negative 10th Teslas. That's the amount of the magnetic field in the x direction, and because it's negative, it means it's going left. I'm not going to put left because negative left would actually be right. Now, B in the y direction would be B1, which points up, plus B3y, which points down. B1 in the B1 would be 1.87 times 10 to the negative 9th Teslas. That's the same value, plus a negative 1.4 times 10 to the negative 9th Teslas. And so if I do that, 1.87 times 10 to the negative 9th minus 1.4 times 10 to the negative 9th, I get 4.7 times 10 to the negative 10th Teslas. Now, I didn't really have to do that because that value and that value are the same numerically. One's just negative, one's positive, and then that's positive and that's negative. So we get the same numerical values right there. But what this means is that it points 4.7 times 10 to the negative 10th up and 4.7 times 10 to the negative 10th that way, which is really cool because if that side and that side are the same, then you know right now that angle's 45 degrees. But it doesn't ask that. It just asks what is the strength. How do I go about determining the strength if I know that side and that side? In other words, how do I add vectors that are perpendicular to each other? I Pythag them. So 4.7 times 10 to the negative 10th Teslas, that would be the x direction squared, plus 4.7 times 10 to the negative 10th Teslas squared, square rooted, or I could just simply multiply that by root 2. So, because remember, 45 is 1 root 2. So if I multiply that value by the square root of 2, I get 6.65 times 10 to the negative 10 Teslas would be the magnitude of the magnetic field there. So that is B total.